Okay, so now we're going to resume our discussion of permutations and cycles. And for this, you're going to need to know what the composition of functions is. So if you're not familiar with that, perhaps from a high school class in algebra or college class in algebra, you probably won't know what I'm talking about. So here goes. Given two permutations, P from the set 1 through n to the set 1 through n, and sigma from the set 1 through n to the set 1 through n, we see that these two permutations are functions that can be composed. That is, the composition P composed with sigma and sigma composed with P are defined. These compositions are referred to as the product, as in multiplication, of P and sigma, and the product of sigma and P respectively. A survey of abstract algebra would explain the curious convention of referring to a composition of functions as a kind of product. However, we're only going to go as far into abstract algebra as we need to understand permutations and cycles so that we can talk about determinants with authority. Okay, so moving right along. Keeping in mind that the product of two permutations is merely a composition of two functions, let us consider the product of cycles 1, 2, 3, 4 and 2, 4. Okay, this product yields the ordering 2, 1, 4, 3. The reason why is as follows. Now I do apologize for the line break there, but those two cycles, they should be right next to each other, as if to suggest that they are being multiplied. But there's a line break there, deal with it. And also, remember from compositions of functions that it's the inside function, or the function that's on the right. You plug a number into that, you get an output number from it, and that output goes into the outside function, which is on the left. So that's how this works too. So the reasons why is as follows. The cycle 2, 4 maps 1 to 1. Right? Because 1 doesn't appear in the cycle, and we're assuming that the cycle's on the set 1 through 4, let's say. So because 1 doesn't appear, 1 is simply mapped to 1. It's left alone, right? And the cycle 1, 2, 3, 4 takes 1 to 2. Hence, 1 is moved to the second position, right? So first, the cycle 2, 4 leaves 1 alone, right? And then the cycle 1, 2, 3, 4 takes 1 and moves it to 2. So 1 ends up, eventually, in the second position. Next, the cycle 2, 4 takes 2 to 4, and then the cycle 1, 2, 3, 4 takes 4 to 1, yielding 2 in the first position, eventually, right? Okay. The cycle 2, 4 takes 3 to 3, because 3 doesn't appear, it just leaves it alone. Then 1, 2, 3, 4 takes 3 and moves it to 4, yielding 3 in the fourth position. Next. And finally, the cycle 2, 4 takes 4 to 2, and then the cycle 1, 2, 3, 4 takes 2 to 3, yielding 4 in the third position. And so if you review all of these steps, you'll notice that what we have is the ordering that we claimed we would get, which is 2 in the first position, 1 in the second position, 4 in the third position, and 3 in the fourth position. So we have the ordering 2, 1, 4, 3, just like we said. And success. Moving along. Now the existence of the identity permutation should be established. That is, there exists a unique permutation, I, from the set 1 through n to the set 1 through n, such that for any permutation, P, going from the set 1 through n to the set 1 through n, we have I times P equals P, which is also equal to P times I. Okay, now to see that this is true, let's just define a function, okay? Simply define I of k equal to k for all k in the set 1 through n. And we have such a permutation, okay? Notice that when we define that function, what happens when you plug in 1? Well, I of 1 is just 1. How about 2? I of 2 is 2. How about 3? I of 3 is 3. So basically, it takes everything and leaves it alone, right? Basically, yes. Okay, since the permutation I yields the ordering 1, 2, 3, blah, 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 n, right? One can think of the permutation I as being the permutation that does nothing. Viewed like this, it should seem obvious that I times p is equal to p, which is also equal to p times I. Okay, we won't deal with that too much more. Moving on. The viewer may already be aware that a function has an inverse if and only if that function is bijective. Since permutations are bijective functions by definition, then every permutation has an inverse permutation. That is, given the permutation alpha, there is a unique permutation alpha inverse with the property that alpha times alpha inverse equals the identity I, which is equal to alpha inverse times alpha, where I is the aforementioned identity permutation, and alpha, with the -1 superscript, is called the inverse of A. Of course, that notation you should recognize if you're familiar with the composition of functions and inverse functions from an algebra class. Moving along. Note that although alpha times alpha inverse is equal to the identity, which is also equal to alpha inverse times alpha, permutations do not necessarily commute. That a permutation and its inverse does commute is a special case arising from the fact that a function and its inverse commute with respect to composition. So that is a special deal. Not all permutations do that. That is, not all products of a permutation and of permutations commute. Okay, and that's all for today. See you next time.